Hi guys, we're having a look at the multiple choice questions 13 to 22 of the VCAA 2014 Maths Methods Exam 2 paper. And these are just my solutions. They're nothing official, but they're just my solutions. Now we're starting off with an absolute doozy of a question. This is CAS at its most CASy, folks. So let's see what we can do with this. We've got the domain of the function h, where h of x equals cos of the log of x with a base a, would you believe, and a is a real number greater than 1, is chosen so that h is a one-to-one function. Which of the following could be the domain? I think basically because we've got an a here, this makes it really abstract and it makes it impossible to graph unless you actually choose a value of a greater than 1, such as 2, and then you can graph the thing and have a look at it. That's something that we can do. So basically I think there are two approaches to this question. The first approach is just to go for the CAS and try to solve for where there are stationary points, and then of course we would have a one-to-one function between any two successive stationary points so that the function was going either up or down, but not both, between two successive stationary points. Or we could just substitute a value for a, such as 2, as I mentioned earlier, and we could try to get a graph of it and have a look at it. Alright? Now the first thing I did was I went for the CAS, and I first of all put the function in, like that, and then I solved it for when the derivative of the function was 0 for x, and I got this funny looking thing here, which actually is quite helpful. This n9 here is just a parameter, so that means we've got a to the something pi, where the something could be any integer. So it could be a to the 0 pi, which would be 1, or a to the negative something pi, or a to the positive something pi. And that immediately, if you just have a little look through these options here, this one, look, there's a 1. It's the only one with a 1 in it on the left-hand end of the interval, and that corresponds to a to the 0 pi, and then a to the pi on 2 would be somewhere between 1 and a to the pi. So that's looking promising, that one there, immediately, okay? So, as I'm saying, if the stationary points are where x equals a to the k pi, where k is an integer value, that is, for example, a to the minus pi, or 1, or a to the pi, or a to the 2 pi, etc., then C obviously fits. This nasty question is confusing because unless a has a specific value, then the function can't be graphed, and it is very abstract. Now, this is the first approach that I've used on this screen, where I'm just going with the CAS and I'm trying to solve it for the derivative of the function equal to 0, and then picking some points or interval between successive stationary points which points us to C, or over the page let a equal 2 and solve it that way, depending on which way you prefer to do it. Alright? So there, in that instance, we're saying the stationary points would be 2 to the 0, 2 to the pi, 2 to the 2 pi, or in fact 2 to the minus pi, 2 to the minus 2 pi, etc. And hence, if we use a instead of 2, we would get this here, okay? C does fit, so therefore 1 to 2 to the pi on 2 would be 1 to 1, and for a graph of it, we can go over the screen. I've actually chosen a equals 2 in this instance, and you can see this here is where x is 2 to the 0 pi, or 1, and this here is a stationary point where we've got x equals 2 to the 1 pi, and then the next one, the next stationary point is over here where x is 2 to the 2 pi, which works out to be 79.51. So we can see that from x going from 1 to a to the pi on 2 is 1 to 1, and therefore the answer is going to be C. Alright? Now question 14. This looks like a very straightforward, nice little question, particularly considering what we've just been doing with question 13. But however, guys, I actually don't think you can do this question the way it's worded. I can't see how you can do it. I don't think there's enough information. So I'll explain why as I go. If x is a random variable such that the probability that x is greater than 5 is a, and the probability that x is greater than 8 is b, then the probability that x is less than 5, given that x is less than 8, is. Now, I actually think that this should be saying the probability that x is less than or equal to 5, given that x is less than or equal to 8. Because it's just a random variable. It's not a continuous random variable, or at least it's not indicated that it's a continuous random variable. And the case where x equals 5 and x equals 8 has been completely omitted. And this is a vital piece of information, because if we want to work out the probability that x is less than 5, it's the complement of the probability of x being greater than or equal to 5, okay? And the probability that x is less than 8 is going to be the complement of the probability that x is greater than or equal to 8. And we're not given the probability that x equals 5 or x equals 8. So I'll go through it as if it was saying the probability that x is less than or equal to 5 given that x is less than or equal to 8. And I'll show you what I got, okay? So the probability that x is less than or equal to 5, given that x is less than or equal to 8, would be the probability that x is less than or equal to 5 and x is less than or equal to 8 over the probability that x is less than or equal to 8, wouldn't it? That's just the multiplication formula of probability, yes? The intersection of x being less than or equal to 5 with x being less than or equal to 8 is in fact x is less than or equal to 5. So the numerator for this here becomes this, alright? So if it was like it is here, if it was worded this way with the equals included in the inequality sign here, then I could do it, okay? And it would just be 1 minus a over 1 minus b, okay? And therefore that's the same as, if you multiply top and bottom by minus 1, would be the same as a minus 1 over b minus 1, which would be E, option E for you and me. But as I say, I actually can't do this question, so I think there's probably a typo in it. Alright, over the screen to question 15 now. Zoe has a rectangular piece of cardboard that is 8 centimetres long and 6 centimetres wide. Zoe cuts squares of side length x centimetres from each of the corners, as shown here. There's 1, 2, 3, 4. They're cut out from the corners of the cardboard as shown in the diagram below. Zoe turns up the sides to form an open box. The value of x for which the volume of the box is a maximum is closest to. Okay. First of all, we should sort this out. This is going to be, this dimension here of what's going to be the floor of the box would be 6 minus 2x. This would be 8 minus 2x. So the volume is going to be 8 minus 2x times 6 minus 2x times x. Alright, this x over here. Alright, so let's work this out. So v is that thing, which is that. I've just taken 2 out of each of the brackets, and we know that x is going to be between 0 and 3. That becomes obvious when you look at it, because if x was more than 3, well, this side becomes negative, which is just a nonsense. And obviously x has to be greater than 0, otherwise we haven't got a box at all. Okay, guys? Right. So we can use CAS to find the value of x when dv dx equals 0 over the page. To find the function, then solve for the derivative equals 0 for x when x is in there, between 0 and 3. I got that, and then I decided to get a decimal value for the same thing, and I got that, alright? So therefore, 1.13, which is closest to B. Alright, on to question 16. The continuous random variable x with probability density function p of x has a mean 2 and a variance 5. The value of this integral here is. Alright, that's a nice straightforward question, guys. So we know that the variance of x is equal to the expected value of x squared minus the expected value of x all squared, isn't it, right? Fleshing that out a bit more, we can say that 5 is equal to the expected value of x squared minus 2 all squared, because we know that the mean is 2, we know the variance is 5, alright? So therefore, the expected value of x squared is 5 plus 4, which is 9, okay? And the definition of the expected value of x squared, ladies and gentlemen, is that, okay? So, and that's what we're asked for. So therefore, the answer is 9, which is C. Alright, over the screen we go to question 17. The simultaneous linear equations ax minus 3y equal 5 and 3x minus ay equals 8 minus a have no solution for. I find the quickest and easiest way to do them is by hand. So there's our first equation, there's our second equation. Let's write it in matrix form, which is the way I like to do them, and solve for the determinant equaling 0. So that's the determinant. It's this one times this one minus this one times this one, and if that equals 0, then we get that, and therefore we get a as plus or minus 3. Now what we need to do now is substitute those values of a, that is plus 3 and minus 3 if necessary, both of them, into these equations here, and just have a look if you've got infinitely many or no solutions, and we're looking for no solutions, guys. So if we substitute minus 3 into equation 1 and 2, we get this one for 1a, that is daughter or son of a of 1, and we get this one, daughter or son of 2. Now this is very interesting because I can see that's a no solution situation, because if you rewrite 2a by multiplying both sides by minus 1, you get that equation there, 2b, which is exactly the same as 1a, except this number on the right hand side is different. So the gradient, the ratio of x to y, is exactly the same in both cases, but this number over here is different, which means the y-intercept is going to be different, which means they have the same gradient, different y-intercept, therefore no solutions. Okay? And by the way, if we substituted a was plus 3 into equations 1 and 2, we would have got infinitely many solutions, which means we would have got exactly the same equations. Alright? So our answer is B. Next question, question 18. The graph of y equals kx minus 4 intersects the graph of y equals x squared plus 2x at two distinct points 4. This is an intersection question. We just need to solve the equations simultaneously, and then we will find that if we set the discriminant equal to a positive value, that means we've got two distinct solutions. Okay, let's do it. There are our two equations. If we equate equation 1 equal to equation 2, we will get this, and then just setting that up like that, we've got that. Now let's work out the discriminant. There it is. It's b squared minus 4ac if the equation was ax squared plus bx plus c equals 0. There's our discriminant. Let's just clean that up a bit. We've got that. And we get that. And we can factorise that as a difference of two squares very easily, and that's going to get us this. Okay, so that is our discriminant in terms of k. So why don't we just draw a picture of that, aka a graph, and we get this. There it is. Now we want the discriminant to be greater than 0 for two solutions. So therefore, in order for the discriminant to be greater than 0, we want this part of the graph here, or this part of the graph here, in other words above the horizontal axis. So therefore the k values which give rise to that would be more than 6 or less than minus 2. Okay, and that gives us answer B. Okay, question 19. Jake and Anita are calculating the area between the graph of y equals root x and the y-axis between y is 0 and y is 4. Jake uses a partitioning shown in the diagram below, which is an approximation technique, while Anita uses a definite integral to find the exact area. The difference between the results obtained by Jake and Anita is... Alright guys, I think we can handle this. It's a little bit different though, because we're dealing with these sideways rectangles, so we've just got to be a little bit careful the way we set this up. Alright, now for Jake, we can label these areas 1, 2, 3 and 4 as I've done there, and then calculate each individual area and then add them up for Jake. But the problem we've got here is that we need to work out these distances here from the y-axis over to the curve, and they are x values. Alright, all of the widths are 1, so that's not a problem, but we need to work out these distances here in every case for each of those 4 areas. So we know that if y equals root x, therefore x will be y squared. Okay, so area 1, if y equals 1, we know that x will be 1 squared, which is 1, and therefore the area is the height times the length, which is 1 times 1, which gets us 1. Area 2, Okay, in that case y is 2, isn't it? Okay, area 2, here it is, y is 2. Therefore x would be 2 squared, which would be 4, and therefore the area would be 1 times 4, which is 4. Area 3, in that case y is 3, isn't it? Yeah, and therefore x is 3 squared, which is 9, therefore the area is going to be 9. And therefore for area 4, y is 4, x will be 4 squared, which is 16, therefore the area is 16. So adding up all of those individual areas 1, 2, 3 and 4, we get 1 plus 4 plus 9 plus 16, which gets us 30. Now let's do Anita's way of doing it now. She's the exact girl. Now for Anita's situation, we have to be very clear about what we're doing here. We are working out the exact area between the y-axis and the curve. So think about these rectangles. Okay, we want infinitely many of these rectangles, each of which has infinitesimal width, and the width is going to be the delta y, and this dimension here is going to be the x, which gets us from the y-axis up to the curve. Alright, so for Anita's situation, we want the integral of x with respect to y. Think about each individual rectangle. The area is x times delta y, and if you have infinitely many of those, then you have the integral of x with respect to y, or x dy if you like, from y equals 0 to 4. Okay, and we know that x is y squared, don't we? So we've got the integral of y squared with respect to y, where y goes from 0 to 4, guys. Okay, happy? Let's go over the screen and finish it off now. So when you integrate y squared with respect to y, you get 1/3 of y cubed, integrated between 0 and 4, and that gets you 64 over 3. Alright, we're nearly there now. We've just got to work out the difference between Jake's and Anita's areas. Now Jake's is an overestimate, as we discovered when we were going through Jake's way of doing it. So therefore, the difference is going to be Jake's minus Anita's, which will be 30, minus 64 over 3, which is going to be 90 minus 64 all over 3, which will be 26 over 3, which is C. Answer C is the one we want. Alright, question 20. This is quite a difficult little question actually. It sort of does your head in a bit until you sort of really see it in the cool light of day when it gives up without a fight. So, make sure you don't get too stressed in an exam setting, otherwise you won't be able to see the wood for the trees and the cool light of day won't come to you. So work on that, guys, through the year. Alright, the graph of a function h is shown below. The average value of h is. Alright, now, it's deceptively simple. Have a look at my little graphic here. So what I'm saying is that this line here, this value here, giving rise to this horizontal line, that is at y equals 7, that gets us the average value of this function. And this, ladies and gentlemen, is why that would be. By selecting the y value of the midpoint of the line segments from 1 and 4 to 6 and 10, that's this first uphill segment here, and again from 6 and 10 down to 11 and 4, we have the average value, because area B, which is above the line y equals 7, is exactly the same as area A, which is below the line y equals 7, and same applies to area C above the line over this side of 6 and 10, and that area C is exactly the same as area D below the line. So if you were to imagine a little hinge here, like a hinge here, and you sliced along there, you could flip-flop that area B right over there to fit into the valley below the line. If you were imagining a road construction project and you shaved off the mountain there above the elevation of y equals 7, you could exactly fit the two bits of the mountain into here and into here, and you would have an exactly horizontal graded road. Well, that's what you're doing with average value. So therefore, guys, y equals 7 is the average height, which is option D. Okay? Question 21. The trapezium ABCD is shown below. The sides AB, BC, and DA, okay, they're all of length P. The size of the acute angle BCD, which is here, is shown as x radians. The area of the trapezium is a maximum when the value of x is. Alright, let's start by putting some flesh on the bones, guys. So if we were to work this out with basic trigonometry, this horizontal length here from this right angle triangle here that I've just created would be P cos x, same thing over here, and this vertical would be P sin x. So let's work out the area of a trapezium now. So it's the average length of the parallel sides times the height. Alright, and the average length of the parallel sides is AB plus CD. Add them up and divide by 2. Alright, easy to do. So we get this. Now just keep your head, get it to a level where you can plug it straight into the CAS and then just go for it. Don't mess about, just use the CAS. Simplifying that, we get that. We get that. Alright, so what is it? P squared times 1 plus cos x all times sin x. So go for the jugular and hit the CAS and set dA by dx equals 0 for the stationary point, which we're assuming will be a maximum. Let's do that. Okay, I've put the value into the CAS handheld there, and I've solved for the derivative equals 0, given that x is between 0 and pi on 2. You have to do that with trig functions, otherwise you'll get general solution gobbledygook. Okay, at least you do on the TI CAS handheld device, which we use in my school, and we get the answer. X is pi on 3, and oh, look, it's there. How marvellous. So the option D is the one we're looking for. Yes? Good. Okay, last but not least, question 22. John and Rebecca are playing darts. The result of each of their throws is independent of the result of any other throw. The probability that John hits the bullseye with a single throw is 1/4, and the probability that Rebecca hits the bullseye with a single throw is 1/2. John has 4 throws and Rebecca has 2 throws. Okay. The ratio of the probability of Rebecca hitting the bullseye at least once to the probability of John hitting the bullseye at least once is. Well, guys, with these kind of things here, we've got these ratios. I like to do them as a fraction, so as I don't get too confused with what I'm doing here, because fractions cancel nicely, and with ratios like this, if you're not used to doing them like fractions, you can get awfully messed up. At least I can. So let me do it as a fraction, and I'll show you how I did it, guys. The probability of no bullseye for John would be 3/4 to the 4. Okay? That's no bullseye, and therefore the probability of at least one bullseye for John would be that. Okay? Now the probability of no bullseye for Rebecca, similarly, she only has 2 throws, so that it would be 1/2 squared. Therefore the probability of at least one bullseye for Rebecca would be that. Alright? Now, we just go for the kill now. The probability required as a fraction would be the probability of Rebecca getting greater than or equal to 1 bullseye over the probability of John getting greater than or equal to 1 bullseye. Now you can go straight for the CAS at this point, but I didn't. I just worked it out, and it's up to you, and I got that. It's looking pretty nasty, but it did simplify very easily. I got that, and I found that cancelled very nicely. So therefore I got 192 over 175, which if you convert to a ratio, remember you've got to have them in the right order, Rebecca to John, would be 192 is to 175, which would be option E. So that's it, guys. That is the 2014 VCAA Maths Methods Exam 2 multiple choice questions now completed. I think question 13 was by far the nastiest, and you would just give that question a wide berth if it confused you, and you would do all the questions you could, and you would come back to that question later. The last thing you would do would be to dwell on it and to lose valuable time. Alright, I hope you got something out of that, and we'll see you soon.